chapter 7. The title is the hydrogen atom. So in this course so far we have learned starting from the particle in a box. We also discussed the rigid rotator and we discussed the harmonic oscillator. And all the models are toy model for understanding the real chemical phenomena. So particle in a box can explain the quantization of energy levels, and harmonic oscillator can describe the vibration motion of diatom molecules, and the rigid rotator can describe the rotation of diatom molecules. So we are going to apply all our understandings to solve the hydrogen atom's Schrödinger equation. So this is like the grand summary. So section 7.1, the Schrödinger equation for a hydrogen atom can be solved exactly. So in the very beginning of our course, I mentioned that in this course we are going to solve 4 toy models using our hands. So that means we don't need any computational powers of computers. So that means we don't need any approximation. We don't need any numerical approximation. So section 7.1 said that the Schrödinger equation for a hydrogen atom can be solved exactly. This means hydrogen atom is also one of the toy model example. So let's think about the structure of hydrogen atom. So the atomic number for hydrogen atom is 1. So there is one nucleus here, and we have only one electron. So electron is here, and the nucleus is here. So basically, this is the two-body problem. So there is a positive charged nucleus. There is a negatively charged electron. And when we see this model, we easily capture the potential energy between the positive charge and negative charge. So this is Coulomb attraction energy. Potential R, which is the distance between the positive charge and negative charge. This will be given as E squared divided by 4 pi epsilon 0 R. So here E is the unit charge of the proton or electron, and the epsilon 0, this is the permittivity of a free space or vacuum. And yes, as I mentioned, R is the distance between the electron and the proton. So with this potential energy, we can write down the Hamiltonian. So Hamiltonian is the sum of the kinetic energy and potential energy. So kinetic energy of electron does not really depend on the system, right? So it can be written same for all other examples. H bar squared divided by the mass of the electron. And we are going to take the second derivative with respect to x, y, and g. So that is the Laplacian operator here. And the potential energy, 4 pi epsilon 0 E squared. So now we have the Hamiltonian for the hydrogen atom. So it is the starting of solving Schrödinger equation, right? So when you know the exact structure of Hamiltonian, that means you can solve Schrödinger equation. So let's write down the Schrödinger equation with this Hamiltonian. So that will be merely just rewriting of this equation. So I want to ask you about symmetry. So we have understood some coordinates such as the Cartesian coordinates and spherical coordinates and polar coordinates. So which coordinates would be appropriate for this problem? So you might easily realize that the Cartesian coordinate is not proper for this system. I mean, the problem would be more difficult to solve with Cartesian coordinate, considering the symmetry of this problem. So this system, the hydrogen atom, it has the central symmetry. It has a central symmetry, right? So that means this system can be more easily described with spherical coordinates, right? So we are going to use the spherical coordinates, and it means that the three independent variables are r, the distance, and the theta and p. And also it changes the form of the Laplacian operator. So del square would be given as 1 over r square. It would be a lengthy expression, but anyway, we are going to write down that. Okay. So we can obtain the explicit expression for the Schrödinger equation if we plug into the Laplacian operator here and the wave function here and there. So anyway, if we plug them into the Schrödinger equation, that would be a very lengthy equation, but we can make some simplification. We are going to multiply the whole equation with 2me r square. And you need some rearrangement of the terms. And the purpose of this rearrangement is that we want to group the terms with a single variable. So let's write down the final result. So it will be h bar square yeah, even for me, it is very complicated. So something like this. Sorry. Do I make any mistake? So we already multiplied the both sides of equation by 2me r squared. So it will be like this. So you might realize that the purpose what I want to do. So we want to separate the terms with involving r term, the terms with the theta and p term, something like that. And some of you may realize this part. This part, they involve only theta and p. So this describes the angular dependency of your Schrödinger equation. And this term is exactly looks like the square of the total angular momentum. So your final Schrödinger equation for a hydrogen atom would be something like this. So maybe you realize that, oh, okay, now we separate the partial differential equation. We can may separate the partial differential equation to ordinary differential equation. So this term involves theta and p, and the first term and the last term involves only with the variables r. Okay, so this is the Schrödinger equation for an hydrogen atom that we want to solve. And before we try to solve this equation, let's talk about the number of nodes in the wave function, especially for the angular part. So I think all of you are very familiar with the concept of node, right? So we are discussing with the orbiters. So it is basically the wave function of atoms or molecules. So node is the point where the amplitude of the wave function becomes zero. So basically it means that there is no probability of finding electrons. Okay? So node plays a very important role when you try to interpret the chemical observation. So it is very important, and let's talk about that. So if you want to understand the number of angular nodes, then we have to separately consider the nodes in the nodes related to theta or the nodes related to p, right? Because the angular motion can be described by these two variables. So first, let's talk about the nodes in theta. So what is the functional form of the theta for angular mode description? So it is some normalization constant with something like this, right? Which is called associated Legendre polynomials. So let's think about the number of nodes in the capital theta. So number of nodes means that the number of points where the function becomes zero, right? and it is strongly correlated with the number of roots, right? So you might remember how to obtain the associate Legendre polynomials from the Legendre polynomial. So it looks like there is some relation. So you are going to differentiate the Legendre polynomial with absolute m times, and you are going to multiply by this function, right? And we are talking the function between x between -1 and 1, right? So the first term does not really contribute to the knots because they become, even though they become 0 at x equal -1 or x equal +1, these 2 points are endpoints, right? This is like the both ends of the standing wave, so we don't really call them as nodes, right? So let's recall the standing wave something like this. So we don't call these 2 points like nodes, right? So those nodes should be placed in between somewhere like here. And we need to examine the Legendre polynomial PL. This is L's order polynomials, which means P0 is just constant, P1 is the term having the highest term in this polynomial is x, and P2 has the highest term as the quadratic term, something like this. So the Legendre polynomial is the L's order polynomial, and they have the roots, the L roots, right? So the L0 doesn't have any root. What about L equal 1? It has one root, right? And quadratic function has 2 roots, something like this. But what about the associated Legendre polynomial? So we are going to differentiate m times, absolute m times. So the number of roots will be decreased by the value of absolute m. So number of nodes in theta will be decreased from L to L minus absolute m. Right. So this is what we have for the angular motion in the theta. And we are going to discuss nodes in P. So we need to take a look at the function form of capital P. So it is like AM multiplied, the normalization constant multiplied by IMP. For sure, M should be the integer number, right? Less or equal to L. But you might think that is there really not for this function? Some of you think like that because the e to the IMP, this by applying the Euler's formula, this is basically cosine MP plus I sine MP. So if you take the magnitude of this complex number, e to the IMP, then that is simply the cosine square plus sine square. Take the square root of this summation. And this should be always 1, right? According to some trigonometric relation. The sum of the cosine square and the sine square with the same argument, they always become 1. So you might think there shouldn't be no's for this part, right? This value is always gives 1. But what we are trying to say here is we don't really play in the complex number plane. So we are living in the real number, and we are living in a real number space. So we always have to take the some step to make this number to be real, right? So we are going to take the real part, or we are going to take the imaginary part. Something like, I guess you understand this part. So that means we can focus on the real part, or we can focus on the imaginary part. So for the real part to be 0, cosine MP should be 0, and for imaginary part to be 0, the sine function should be 0. So this means that the argument of the cosine function MP should correspond to k plus half multiplied by pi, right? So cosine function becomes half of pi, 3 half of pi here, right? So k should be 0, 1, dot, 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 up to 2m minus 1, because p corresponds to a rotation on the xy plane. So one rotation of p corresponds to 0 up to 2 pi. And what about the sine part? So here the sine function becomes 0 for the integer multiples of pi. So simply this is k pi, and k equal to 1 to dot 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 up to 2m, because of the restriction on the p here. So up to here you might think that, oh, there are 2m nodes along the p motion, right? We are going to remove the 0. Only the positive integer from 1 to 2m would be valid. But I want to emphasize that, so now we are talking about the plane, right? So even though I described the knots as some point, but actually we are talking about the some plane, because we are now discussing some plane along the value of the p. So it is basically the plane. So that means when I say some plane with the function of p, and it would be exactly same as the some function p plus pi. So let's say this function corresponds to So let's say if you are rotate by pi, this plane, then the plane's up ends the plane's up and bottom will be reversed, but anyway the plane would be same, right? So the rotation of pi of the for the plane does not really affect the result. So there are twofold degeneracy. So these are all these nodes are non-unique. So we need to divide them by 2. So actually there are only m nodes here. So the number of nodes in P would be m. So here m is the positive number, right? So we are going to add up the number of nodes in both like in theta and P. So it would be L minus m, and m should be positive number here. And number of nodes in P is m, so L minus m plus m should be L. If we assume that m is the positive number, and this assumption is very reasonable. So I guess some of you may heard that the number of nodes in the angular part is equal to L in a general chemistry textbook, or even some of you may heard that in high school chemistry classes. And actually it is derived from the Schrödinger equation for a hydrogen atom. So if you understand the structure of the angular part of the hydrogen atom's Schrödinger equation, then you can easily explain why there is the L nodes along the angular part. Okay. So this will be, now it's time to talk about radial equation for the H atom. So even though we haven't discussed the angular part yet, but we already know the answer. So angular part can be described by the spherical harmonics, right? So the wave function r, theta, and p, this can be described by the multiplication of the radial part, capital R, and the spherical harmonics. So even though we haven't derived that the angular part should be described by the spherical harmonics, but according to the structure of the Hamiltonian of the hydrogen atom, so if you go back to the previous page, then there is a operator of the total angular momentum square, right? So that should have the eigenfunction of the spherical harmonics. So that's why we have the spherical harmonics here. And anyway, this can be done with the separation of variables. So all you have to do to find out the differential equation for the radial part, you have to plug this relation into the wave function psi. So that means you are going to plug them into the Schrödinger equation. So you are going to have So basically, the first term and some terms in the square brackets, they just from the previous Schrödinger equation. And you may feel like, oh, I haven't seen this term before. But if you think a little bit more, this is basically just the denominator. This is just the eigenvalue of the L square operator, right? So you have utilized that part. So this is the Schrödinger equation for the radial part of the hydrogen atom. And from this relation, you may realize that the total energy E, this value, the total energy, consists of three terms. So the first term, the radial kinetic energy, this one, the radial kinetic energy. So even though it is not really precisely accurate term, but this is related to the angular motion. So we call that angular kinetic energy. And the last term is the potential energy. And before we try to derive the form of the radial part wave function and its eigenvalue, let's write down the final result. So energy of the hydrogen atom depends on the quantum number n, and its explicit expression is something given like this, and should be the positive number. And the function form of the radial part depends on two quantum number, n and l. This is very complicated expression, so I'm not going to write down the whole expression. So there is normalization constant NL, and we have R to L, and exponential function minus R over NA0, and Laguerre function n plus L to L plus 1, and its argument is 2R over NA0. This is called Laguerre function. So I think this is the final result you have seen in the physical chemistry and general chemistry in maybe in high school chemistry textbooks. So this is like more advanced course of physical chemistry, so we have to take one step forward to understand why we have such a weird form for the radial part of the hydrogen atom. So let's derive that. So let's write down the Schrödinger equation for the radial part here. I'm sorry that I have rewrite the same expression so many times. We have to solve this differential equation to obtain the function, explicit function form for R. So we are going to rearrange the functional form. So if you combine the first term and the first term in the square bracket, they share some common parts. So h bar square divided by 2MER square, this part, they shared this part. And you make the equation more cleanly. So final form would be ddr r squared dr. So this is merely the rearrangement of the first equation. So now we are going to apply some technique. So if you take the derivative of the very first term, then you will have the second derivative and first derivative, right? Also, you have the function itself. So the problem is like a little bit complicated. So we want to eliminate the first derivative without any affecting the final result. So you can do that with some change of functions. So instead of r, so you are going to define ur, which is defined as the small r multiplied by capital R. So now we want to change the problem of solving the differential equation for capital R, from solving the capital R to solving small u. Okay? So you can take the first derivative, you can take the second derivative from this equation. So I'm not going to write down the whole steps, but your final result looks like d square u dr square So as I mentioned, so this equation for capital R, now it becomes the equation for small u. And you may feel like this equation is a little bit more easier, a little bit easier to solve compared to the first one, because we now reduced this part like here. So it becomes more concise, right? So it makes you feel this equation is a little bit more to solvable. Okay, now we are going to examine the asymptotic behavior. Asymptotic. So when you try to solve very complex differential equation, the one way to approach that problem is to examine the both ends. Like you want to know the function form when r is very, very small or when r is very, very large. So that gives you some function form. So along the independent variable r, so you want to plot function u. So this region corresponds to r is converged to 0, and this region corresponds to r diverges to infinity. So we try to understand the functional behavior at both ends. Let's say r approaches to 0. So in here, we have the second derivative. And among these three terms, like this one, and this one, which one will survive? Which one will be dominating when r goes to 0? So first term doesn't really involve with r, so they can be considered as constant. And second term and the third term, they involve r. They have r. The second term is proportional to 1 over r, and the last term is proportional to 1 over r squared. So which one will be dominating when r goes to 0? The last term, right? So we can ignore the first and second term and something like this. So when you try to solve this type of partial differential equation, you can just assume that u is the R2S, and you can put this function into the position of u. Then you can obtain some auxiliary equation, so s minus 1, r to s minus 2, because you differentiate the r to s second 2 times. So s and s minus 1 here, and l plus 1 r s minus 2 because of 1 of r squared term here. This is the auxiliary equation to obtain the power s. So to this equation to be valid regardless of the value r, so s should be l plus 1 or l should be minus l. S should be minus l. Right. So you can just cancel these two terms, and to have the valid equation, s should be l plus 1 and s should be minus l. Then you have to think about that, which one is valid. So first choice will give you R2 L plus 1, and the second choice will give you R2 minus L. And one of them is not physically sensible. Can you name which one is inappropriate to describe the hydrogen atoms? It should be R2 minus L, right? So when you make the R, try to, So when you allowed R approach to 0, then this function goes to diverge, right? This function diverges, and the divergent wave function is not really allowed for wave function. So we are not going to accept, and we are going to reject minus L, and L plus 1 is only possible option. And so we are going to examine R goes to infinity. So here we can ignore the second and the third term because they are proportional to 1 over R or 1 over R squared. So when R goes to infinity, they become 0, right? They become 0. So we can ignore them, and we only have the first term, like this one. So d square u dr square plus h bar square to m e u equal to 0. So let's put that. Square root of minus 2me divided by h bar square, h bar as kappa. So this looks very similar to k, but not really k. So because we have k later, so this is kappa. So when kappa is a little bit smaller and k is like taller. Okay. So anyway, with the introduction of the kappa, this differential equation is like kappa square u. So you have already, I guess you already have the experience to solve this differential equation. So u can be exponential plus kappa u or exponential to minus kappa u. So again, one of them is not physically acceptable, and which one would be that? Oh, so sorry. So here should be r here. Here should be r. So one is physically unacceptable. Which one is that? So now we are discussing when r goes to infinity. So what about the first function? If you allow the r value goes to infinity, the function also goes to infinity, right? And remember that the u is the candidate for the wave function of the hydrogen atom, and the wave function can never go to infinity because the square of your wave function is always corresponding to the probability. So probability of the infinity doesn't really make sense, right? So we have to reject the first choice, and the second choice is the only possible option. So now we have the function u as r to l plus 1 and exponential minus kappa r. So we know the behavior at both ends, but we still don't know how this function behavior in this middle region, right? So let's say this region can be described by function fr. So your u function is given like this. So again, we are going to apply the second change of variables. So now, yes, it's step 3. Change of. Actually, this is the first time, right? The first time we changed the function. Now we change the variable. So now we want to play with rho instead of r. Rho, which is defined as 2 kappa r. So when we change the function or when we change the variables, it's all about making the problems simpler and easier to solve. Okay? So with this relation, you can redefine the differential equation, and this this requires tedious mathematical steps, and I will just tell you the final result. So it's rho d square f d rho square 2l plus 1 minus rho df d rho. So because now the function is changed from u to f, because we already have set u as the multiplication of r exponential and fr. So you can plug this into the original differential equation, and you are going to change the variables according to this relation, u equal to kappa r. So this is your new equation to solve. And we are almost done. So even in our mathematics for chemistry course, we discussed many orthogonal polynomials, like Hermite polynomials for harmonic oscillator, and the Legendre polynomial for the rigid rotator. But even in that course, we usually don't talk about the Laguerre function. This is where the Laguerre function comes in. Actually, the Laguerre function is the solution of this differential equation. So let's write down the Laguerre's equation in a more well-known common form. So this is the Laguerre's equation, and solution for this equation is Laguerre function with nth order with parameter alpha, nr. So now we are going to compare the well-known expression of the Laguerre equation, the second equation, with our differential equation. So you may easily realize that rho corresponds to x, right? And f, your function, corresponds to y. And alpha, alpha in the original Laguerre function would correspond to 2l plus 1 here, because this is 2l plus 2. So we break down 2 as 1 plus 1. So this one corresponds to alpha and plus 1 here. And nr here, this one should be the coefficients multiplied in front of the function itself. So lambda divided by k minus l minus 1. And so far we have derived the function form of the radial part, and we now try to understand the restriction on quantum number. So to understand that one, so we have to have some experience in solving this Laguerre function, Laguerre's differential equation. So if you don't know how to solve the differential equation, the easiest approach is to apply the power series solution. So you just put yx as the infinite sum of the polynomial from n equal to 0, a n, x n. So you can take the second derivative and you can take the first and second derivative, which are required for here and here. And you can just plug the power series solution expression into here and there. And you might have some equation like alpha plus 1, A1, NR, A0. And from n equal 1, n plus 1, n plus alpha plus 1, a n plus 1, I don't think we nr minus n a n should be 0. Sorry. xn should be 0. So this is the final result when you plug all the power series solution into the original Laguerre equation. And so you have some freedom to set the constant A0, so it doesn't really matter and it doesn't really affect the quality of your solution. And A1, so we want to have this equation always be equal to 0. So you can just put the A1 to be minus alpha nr divided by alpha plus 1, right? From here. A1 should cancel the A0, right? And what about the coefficients for xn? So all the coefficients corresponding to the polynomial xn should be 0, right? So this is only possibility to make this equation to be valid, right? So let's just say ax plus bx squared cx squared dx cx cube and dx quart equal to 0. So this goes to infinity. So the only possible way to the sum of the infinite, the only way to make this infinite sum to be 0 is let's put a equals 0, b equals 0, c, d, all the coefficients in front of the polynomial function should be 0, right? So with this in mind, let's take a look at the green box here. So from here, you will realize that n plus 1 and alpha plus 1, a n plus 1, that should be equal to minus nr. I mean, just let's just say this plus nr minus na should be 0. So you can find some recursion formula between a n plus 1 and a n from here. So a n plus 1, which means the term next to a n, it should be defined this way: n plus 1, n plus alpha plus 1 minus nr minus n a n. So yeah, it looks very complicated. Yeah, please understand. So let's write down the explicit expression for the case where n is larger than 1. So in that case, y should be a0 multiplied by 1 and alpha plus 1 and r a0. So you may realize that this corresponds to a1, right, from this relation. And from if you want to obtain a2, then you can just put a1 here. So n, you can just put 1 instead of n here. Then that will give you a2. So structure of a2 is nr, 1 minus nr, divided by 2 alpha plus 1, alpha plus 2, x square. So actually, sorry, so this should be x, right? a1 should be a0 multiplied by nr divided by alpha 1, alpha plus 1. And this should be a2, right? So I will write down one more term. 2, 3, alpha plus 1, alpha plus 2, alpha plus 3, and nr, 1 minus nr, 2 minus nr, x3. So basically, this is the infinite sum, as you may see here. This is infinite sum. So we always have to remember that we are not solving this problem for the interest of mathematics. Why do we solve this problem now? We are solving this problem to obtain the wave function for the hydrogen atom. Right. So wave function it cannot really be the infinite sum of some polynomials, right? It should be decay to the 0 at some points, right? So we cannot never accept the infinite sum for the wave function. So that means this function should truncate at some point, and the only possibility to truncate this function is nr equal to 1, because we are not thinking about the case of nr equal to 0. Because if nr equal to 0, then all the terms, the first order polynomial, second order, third order, all the terms will vanish. Then we just have the constant term. So it doesn't really helpful for describing hydrogen atom. So we are reject this case. And what about nr equal to 1? So we only have the first and second term. And third term will vanish because of this term. Right? We can, and what about the next term? Next term always have the 1 minus nr, because due to this recursion formula, right? If the an contains some specific part, then that will remain all the way up to infinity, right? So nr equal to 1, it is okay. And what about nr equal to 2? So now we have one more term compared to the case of nr equal to 1, right? So now we have the first, second, and third term. And for this case, from the third order polynomial, all the polynomial will vanish due to this term, right? And same story. So when nr equal to 3, we have the 4 terms, and from the terms 5, all the terms will vanish, something like this, right? So Oh, sorry. So, actually, so I have to correct myself. So actually, nr equal 0 has meaning because even though y becomes just constant, so y itself is not a wave function, right? So if you go back to some previous pages, then you actually, this is multiplication of the r to l plus 1 and exponential kappa r and function f. And actually we are solving for f. So even though this is the constant, we still have some polynomial structure. So yeah, so nr equal to 0 is still acceptable. So nr should be 0, 1, 2, something like this. So lambda divided by k minus l minus 1 is equal to nr. And due to some relation with the energies, we are going to define the lambda divided by k. So here is, this is k. We are going to set this as n. So actually this is the quantum number that is known as the principal quantum number. Principal quantum number. So principal quantum number is simply the nr plus l plus 1. So L can be varied from 0 to 1, 2, 3, 4, 5 something, and NR also varied from 0, 1 to something. So that's why we have the principal quantum number starting from 1, and it always have to be some positive integer, right? So NR is the positive integer including 0, and L is also can be a positive integer with 0. So it n should start from 1 because of this term, and it should be some positive integer number, right? So so the restriction on the Laguerre polynomial to be valid and to be finite summation of the polynomials. So we have some restriction on on n. So that is the origin of the restriction on quantum number n. And I omitted some derivations, so we haven't discussed the form of the lambda, but actually it was my mistake. So there was some bad notation on my note. So actually this is kappa, sorry. Kappa. So kappa was defined as square root of minus 2me divided by h bar. And the lambda is me square 4 pi epsilon 0 h bar square. So we defined this ratio as n. And from this relation, you can define the energy E in terms of the common constant, such as the mass and the unit charge, permittivity, reduced Planck constant, and pi. So final expression is minus MEE4 32 pi square epsilon 0 square h bar square multiplied by 1 over n square. So this is the exact expression that we have shown in the very first, the previous page. And this is the energy of your hydrogen atom according to the quantum number n. So now we have obtained the energies, and your function UR, this is R L plus 1 exponential minus kappa R, and the Laguerre function 2R and I guess 2 kappa R, right? And but U is not actually the radial part. Radial part, capital R, is actually UR divided by R, right? So this is the very first step that we apply to solve this differential equation. So we define the function U as the multiplication of the capital R with variable R. So now we are reversing that process. So you are going to divide this function by by R. So R to L, exponential kappa R, and Laguerre function here. So actually there is no k in this derivation. So all the k looks like is actually kappa. So please understand my wrong explanation. Okay. And I want to emphasize the finer things. So I know that I already used all of my time, but so now we know the restriction for the principal quantum number n, right? But we haven't discussed the restriction on quantum number L. So even though we know that this will start from 0, 1, 2, something like that, but we haven't discussed the upper limit of this value, this quantum number. But actually, the answer is behind here. The Laguerre function 2L plus 1, m minus L minus 1. So this function is the order of n minus L minus 1. So this is what n minus L minus 1's order polynomial. So that being said, n minus L minus 1 could not be lower to 0.